Hey guys, this is our week 2 review video for Gen Chem. So we are doing the end of our unit right now. We're closing up. So what I'm going to do with our review video is essentially just go through the study guide and kind of talk through it. The study guide is posted on Classroom, so use that if you need to. Sorry, I'm just like seeing people walk by. I'm being nosy. Yeah, you can follow along with me if you want to right now on the study guide, or you can just listen, absorb, and let it happen. All right, so let's see what we got. So in section 1, it says know the difference between exothermic and endothermic reactions. So exothermic reactions, energy is given off or it exits. Endothermic energy goes in or it enters. Identify and label graphs of each. So an exothermic reaction, if we're looking for an exothermic reaction, it's going to start high and then go down. So this would be the energy level of our reactants, boop, energy level of our products, boop, products goes down. So the energy was up here to begin with, now it's down here. Now it's down at the bottom, so the energy has gone down, which means energy must have left the system. It had to have gone out of the chemicals to have left the system or ended up at a lower stage. So the delta H for that would be negative. So if something loses energy, that means its overall energy went down. So if my normal energy is right here and I gain energy, then it's going to be positive. If I lose energy, it's going to go into the negative. So it goes down from what my normal energy would be. An endothermic reaction is going to be the opposite, where we start low and then we end reactants, products with a delta H that is positive. Okay. So an endothermic reaction, the products are higher than the reactants, so it took energy in and has gone up. So the delta H went from base state up, so it is positive. Okay. Know the 4 things that can affect reaction rate and what they do to change the rate using collision theory. Okay, so I will wink, wink, hint, hint, prepare for that because that's basically one of the questions. But prepare for that. So the 4 things are temperature. So as temperature goes up, the particles move around faster and more frequently, and that leads to the higher probability of collisions. So we're going to see more collisions as a result. Concentration, more particles. So if I increase the concentration, more particles means more likelihood for collisions. The third one is surface area or particle size. So if I increase surface area by making the particles smaller, then I can expect that they would collide more. So think about, dropping a sugar cube into a cup of coffee versus dropping a spoonful of granulated sugar. All of those individual pieces are going to start dissolving at once versus the cube, which only the outside does. So more collisions on the smaller particles with the water that's attempting to dissolve it. So all 3 of those really obviously directly affect collisions, and as collisions go up, reaction rate goes up, and that kind of makes sense. Particles can't react until they run into each other, and so if we can increase the likelihood of them running into each other, then we can increase the overall likelihood of the reaction speeding up. The 4th one is catalysts. Now, catalysts don't necessarily cause a huge impact on collisions. What catalysts do is they just provide activation energy. So they do cause collisions because activation energy really is saying, okay, how much energy do I need to have in these particles when they run into each other to make them react? Okay, that's what activation energy is. How much energy has to be there to get them to react when they collide. So catalysts basically kind of provide some of that energy in a number of different ways, but they provide some of that energy. So they do get the particles to already start with a higher level of energy. So as they gain activation energy, they don't have to gain as much. Know how to identify the change that occurs on a reaction curve after adding a catalyst. So as mentioned, it reduces the activation energy. So if I had, ooh, that's ugly. If I had a reaction like this, where I started with my reactants, ended with products, okay? So if I had reactants and products like that, then the activation energy is essentially getting up to there. So I have to get up there from where I started, whatever, you get the idea. So a catalyst would essentially just say, oh, yeah, you don't really have to go as high anymore. So you don't have to gain as much. You still have to gain some. We still got to get these particles moving, but they don't have to be like grooving too much. They can just get a little bit of energy, all right? Know how to convert from Celsius to Kelvin. From the Celsius to Kelvin scale, it's Celsius plus 273. It's on your placemat. It's not on the exam. Don't worry about it. Who cares? Know the formula for calculating heat energy in a reaction and what each variable stands for. Be able to define each variable and identify correct units. So calculating energy of a reaction is essentially calculating delta H. So we use the equation delta H equals m delta T Cp. That is on your placemat, so you don't need to worry so much about remembering it. But do realize that delta H is overall basically change in... I can't spell. Change in energy. M is mass. Temperature is change in temp. Big point of information there. It's always... final minus initial, and then specific heat capacity for CP. I may have spelled it right, whatever. So delta H is change in energy. That is going to be measured in joules. So just capital J, joules. Could be in kilojoules, but we don't use kilojoules really. Kilojoules would show up a lot in physics, but most of the time we're using joules because it's a pretty small reaction. So delta H is change in energy, which is measured in joules. Mass is going to be in grams, like most masses we work with. Temperature is either going to be degrees Celsius or it could be in kelvins. Oftentimes, it's probably going to be in degrees Celsius, but it doesn't really matter which one they're in as long as they're both in the same thing. And then specific heat capacity is joules per gram Kelvin or joules per gram degrees Celsius. Okay, so the unit there, joules over grams Kelvin and joules over grams degrees Celsius. Okay. So those are the correct units. It says be able to solve for any variable. That's basic algebra. So make sure that you are recognizing if something is multiplying, you need to divide it to get rid of it. Next thing. Recognize how specific heat affects the rate at which a substance will heat or cool. So specific heat capacity is describing how much energy it takes to raise the temperature of 1 gram of that substance. So if it takes 1 joule to raise 1 gram by 1 degree Celsius, and something else takes 5 joules to raise that 1 gram by 1 degree Celsius, the one with 5 joules takes a lot more energy, which means it's going to heat up really slow. No matter what you're really doing to it, if it's receiving the same energy as something else, it's going to be slower to heat up. Water is a great example. Water has a really high specific heat capacity, which means it can hold a lot of heat before you see a temperature change. High specific heat capacity, that's how I remember it, high capacity, saying, oh, okay, this substance, if it has a high number for specific heat capacity, then it can hold a lot of energy. It has a high capacity for energy, which means it's going to heat up pretty slow, because if it heated up fast, it would get really hot and it would boil off, and that just wouldn't work. So it must heat up very slow as it's absorbing all of that energy. Be able to identify substance based on their specific heats. Essentially, if you're solving for a CP and then you're given a chart that says, here's some CPs, which one is it? It's matching. So it should be pretty straightforward. Identify if a substance has a high or low specific heat capacity. So again, that goes on a graph, excuse me. So again, that goes back to if it's going up very slowly, if it's going up very slowly, that means it's taking in a lot of energy to raise its temperature, which means it does have a high capacity for heat. If it's going up very quickly, it means it does not have a high capacity for heat. And then we get to calorimetry. So the whole idea behind calorimetry is not meant to be anything super chaotic. It's just saying, you know what, it's really difficult to measure how much energy is actually leaving a reaction, because it's lost to the air, it's lost to the atmosphere, it's lost to the table. So what if we have the reaction occur inside of a chamber where we can capture most of that energy to calculate it? That's what calorimetry is. So the idea behind calorimetry, again, is we have, usually it's 2 cups or something nested in one another. That's not a cup. And then what we do is we put water inside of it, and then in here is where the reaction is going to occur. And as long as we can as long as we can observe what the temperature changes within the water, we can determine, well, okay, if the water gained a certain amount of energy, then that must be what this gave off, because it couldn't have gone really anywhere else other than into the water. No, it's not perfect, but other than going into the water, the energy really couldn't have escaped any other way. So all of the energy that the water absorbed must be what the reaction gave off, or vice versa. If the water cooled down and lost energy, it means the reaction must have taken that energy in. So that's the whole idea of calorimetry, is just saying, how can we make something that's really difficult easier? And so it's really difficult to measure energy given off by a reaction. So what if we do it inside of something else? And then we can measure it that way. So that's what we did. So you start a calorimetry problem, you have to start really by saying, okay, well, what happened to the water? So I noticed those of you that were turning in your labs early, a lot of us were using the wrong masses for the water, because the first thing you're supposed to do is worry about the water itself. And in the lab, that was 100 grams of water, but a lot of you plugged in 4. I don't know why. You just read 2 different things and pretended like they were the same thing and went with it. I don't know. It happens. But those of you that did it when you sent it in early, I kicked it back to you so that you could fix that, because, yeah, that was going to be kind of devastating to that grade, which could be a problem. So I got you back. But make sure that you're starting with water, and then you essentially just flip the sign. So if I say, okay, 5 people walked into the building. Okay, well, then how many people left the outdoors? 5. Okay, cool. So the building went up by 5 and the outdoors went down by 5? Yeah, okay. That's exactly what's happening in calorimetry. So if I say, okay, the water absorbed 10 joules of energy, okay, well then whatever went in it lost 10, period. So if the water gained 10 and went up by 10, it's positive 10. And if the reaction then lost 10, it's negative 10. Be able to perform calorimetry equations showing any of the variables, solving for any of the variables in a delta H problem. So basically that is just reworking it to make sure that it fits. You can solve for anything in the equation. A lot of times what will generally be is it'll say, oh, we have an unknown metal. Let's drop it in the water, see what happens to the water, and use that to determine what the metal is. So just like we did in our lab before we left on break, where we took the metal, I don't know why I'm hugging this, where we took the metals and dropped them into the water and then calculated how much energy the water absorbed, made it negative, and that's how much the metal lost. So that's essentially how it goes. So your exam for this unit is being posted tonight at midnight. I'll probably post it a little bit before then, probably at like 4 or 5 today. Please don't cheat. I know you have the option to. Now, let me clarify. It's an open notes exam. I'm well aware of that. Duh. Okay, of course it is. What I mean by don't cheat is don't just like work on it with someone. Please try to do it on your own, because even if there's material you don't remember, I want you to find it in your notes, of course, answer the question. And then I put in there, I really want you to go through and highlight in your notes the things that you had to look up, because we're continuing our distance learning until the end of April, which means it's going to be getting really close to finals. And I want to make sure that when you're preparing for finals, you know exactly what you struggled with. Because if you know endo versus exo, then you shouldn't have to study that again. We've had enough going on this year. We don't need to review things that we already know, right? So make sure that when you do your exam, find a quiet place or listen to music, whatever you need to do. You can have your notes out, take your exam by yourself, and then look up what you need to, but make sure you identify and you reflect to yourself on what you needed. Okay? All righty. Good luck on it, and I will see you guys soon.